conductivity is lower than about 0.5, electrons are both pretty equally connected to non-polar covalent bonds. If it's bigger than 0.5 but smaller than around 0.7, one of the elements is pulling off the electrons pretty hard. Not quite hard enough to completely steal an electron, but definitely hard enough to skew the electrons a bit, making it a polar covalent bond. An example is water. Oxygen has a very high electronegativity compared to hydrogen. As a result, it pulls the electrons of hydrogen so hard that they kind of belong to oxygen, giving it a partial negative charge, and hydrogen with a partial positive charge. The presence of two poles with opposite charge is called an electric dipole. All permanent dipole molecules can interact with each other, and really with anything that has a charge. As a result, the molecules will tug on each other and arrange themselves in a way that oppositely charged ends are next to each other. The forces acting between them are called intermolecular forces, or IMFs. A specific example is hydrogen bonds, where hydrogen bonds to something very electronegative, like fluorine, oxygen, or nitrogen, creating strong dipoles that tug on each other. But even if molecules are not polar at all, there can be electrostatic forces acting between them. How? Electrons move around inside the atoms, and by pure chance, they can end up on one side of the atom, creating a momentary dipole, which influences other particles next to it to become a dipole as well. At least for a very short time, as the electrons keep moving and the dipole disappears. This is called the van der Waals forces. The polarity of water also explains why it's one of the most versatile solvents to exist. It can pull apart molecules by tugging on charges, and it keeps them apart by surrounding a particle with its oppositely charged end. Water cannot dissolve nonpolar molecules though. It's the reason why water and oil don't mix, since fat molecules are nonpolar while water is polar. Just remember the ancient saying, similia similibus solventur. Or in the language that's actually spoken, similar things will dissolve similar things. Fun fact, soap works because the molecules that it's made from, which are called surfactants, have a polar head and a nonpolar tail. This way, when in water, they can surround, for example, nonpolar fat molecules and form micelles, which, along with the water, transport the dirt particles away. These are the most important bonds and forces ranked by strength: ionic bonds, covalent bonds, metallic bonds, hydrogen bonds, and van der Waals forces. There are three main states of matter: solid, liquid, and gas. Solids are tightly packed in fixed structures, where the particles can only wiggle, unless, you smash them. In liquids, the particles can move freely but are still confined to a fixed volume, as the forces between them are still strong enough to keep them together, and the particles in gases have enough energy to just do whatever they want and fill up all the volume you give them. Knowing this, we can find two important words. Temperature is the average kinetic energy of particles in a system, or how much and how fast they move, and entropy is the amount of disorder. Substances tend to be solid at low temperature and or high pressure, which is a state of low entropy, as they're neatly organized and don't move that much, and gas at high temperature and or low pressure, where they move around like crazy, so it's a state of high entropy. Strong bonds, like ionic bonds, lead to high melting points, as they take a lot of energy and therefore a high temperature to break apart. That's why most salts are solid at room temperature, whereas water, which is only being held together by hydrogen bonds, is a liquid. Well, actually, there's another state called plasma, which is